Hi, I'm Dr. Alexander NGENZI from University of Rwanda College of Science and Technology, Department of Computer and Software Engineering. So if it is I, D, T, F, T, which the inverse of the other is going to be, of course, the period in case of 1 over n is going to be 1 over pi. So it's going to, so in case, instead of just having 1 over n, it's going to be the x of n is going to be 1 over 2 pi in this case. And you integrate because you are trying to get the interval from 2 pi to pi, or to any value of big X to big X of the other value of ours. Remember, it is in discrete value domain. This is what we had from the beginning. Then you multiply this very big N, a big W, dW. So with respect to W. So remember, these values are going to change. You want to obtain X at JW, big W. So these are very useful. For example, you want to bring you have your frequency domain. You want to obtain X of n, but you have to integrate with respect to these big omegas. And you remember the omega sign, which I said, for example, if this omega is going to be this 2 pi over n. This one can be also a period, can be k, any periodic signal of any paired discrete time signal can be transformed. So in general, or in summary, to summarize this, the relationship between Dtft and Dft is that, for example, you have, so now we are going to see the relationship. So suppose if you have Dtf, Ft, you can have x of n, this is small x, converted to big X of e power j of big omega. So like this, in this case. But you can also having x, big X, small x of n, that is, you want to use dt, discrete time, discrete time of Fourier transform, DFT. You can just easily get the big, this is very easy. So you get the big X of k of n. So in this value, so this is very easy. So you can see, using putting the time domain makes it to bring the other content where you may need omega, which is transformed, for example, the time, for example, in this case. So the frequency, for example, it's a half of the time. So if you transform the time as given, then you can put 1 over 2 pi, for example, times the other way around. So it's going to be omega over 2 pi, isn't it? So you can see all these relationships can also, they matter a lot. So in this case, having derivative this one also, you can have big X of e or j omega, that is, remember, from negative infinity, n is going to be negative infinity to infinity of So it's going to be very important. So in this case, if we say, for example, having j omega n in this case, then you can have such a kind of values in this case. This is a discrete value that's going to have a very important relation. So this is very important in terms of, for example, you want to obtain this form. Of course, in general, you can have big X of k that is going to be summation of any value from n is equal to, and remember these are the notion that we used even before. From x, this is the small x of n times big W n k of n, or yeah. So this is a DFT. So one is Dtft, but another one is also DFT. So to obtain their corresponding values. I hope these relationships are handy. Bear in mind that omega n has its value, and it is nothing but omega n is going to be e power 2 pi kn, or depending to which value over n. So this is very important. This one also is very important to know. So all these relationships, suppose if you are given any number, or if you go inside your tutorials, you can easily calculate them. And as I said, this is also true. This is also true. You will remember. Yeah. So we can continue from there. So if you compare, now if I say, for example, compare, if I say, for example, in comparison, see if you compare Dtft with and the Dft in general, so by comparing them. So let us compare and see how they are somehow related. For example, if I bring this factor, the other factor of j omega n is going to be the big N in this case, but having this value. So that is number one. But also this one also can be converted into e power 2 pi j 2 pi over n, but also putting these values also. So kn is going to appear on this. So these are like relationship, how they are related. So as we know, this omega big N is going to be e power j 2 pi of n. That one is very common. So we can conclude that W for omega is going to be 2 pi big K or K of n. This one also is very common. So why are we just elaborating this one? It is going to help us during our calculation. Suppose if we are given any number, as we start to see it in our first chapter, this is going to be very much occurring. It's going to appear as much as possible. So it's going to happen every time in our calculations. So having this in mind, you will just remember them, then bring them on the board, then you can you can just have a quick remind of what is there. So having all this, we have this omega, we have everything given. There is this one, there is this one. So we want to bring them and combine them. So in case if you have x of k, that is the frequency domain, is also x of j omega. In this case, from where omega value is going to be, remember 2 pi k over n, whereby you are going to obtain the general value of summation from n equal to 0 of big n minus 1 plus the small x of n, in this case then e power the other value of our. So it's going to be 2 pi over n times 2k of n. So 2 pi k 2 pi kn, sorry, and then should be also kn. So this is very important, and this is what we have been discussing even from the beginning. So it's very important. Yeah. So we are compare them and see the relationship between them. So having described what is n, what is omega, what is big omega n, what is k, what everything is described here. Yeah. So this is very important to note. Yeah. So in a comparison here, if I say compare Dtft with Dft comparison, this one also is a comparison, but the main comparison here at Dtft, you can see there is a continuous appearing of omega in this case. And the continuous appearing of omega on this case doesn't appear here. At Dft, we are going to have a discrete frequency. We have a bunch of frequencies, as we say, but we want to decompose them or divide them or just divide them into small pieces so that it can be well managed. That is the difference. Another difference is that you can see the sampling of Dtft can be divided in non time domain. Of course, the sampling of these values is going to be number one, the different, and now we are comparing. So comparison of Dtft with Dft. So number one, we say there is a concurrence or just an appearance of omega in all your functions. So the continuous function of omega is existing. There is much appearance of omega function. But on the other side, it should be discrete frequency domain is all spectrum can be observed. Another difference is we can use sampling in time domain. Sampling is in time domain, but the other side it can obtain by performing sampling of the both time. So the other one DFT, the sampling can appear in both domains, time and frequency domains. So those are the comparisons. So on DTFT, it cannot be computed or analyzed numerically. So you cannot use number in DTFT based on infinity sequence of x of n. So here you cannot obtain the analysis cannot be numerical analysis. Okay, it is not numerical analyzed. So the analysis cannot be used in infinite frequencies. So for example, if we have extending to the value, for example, having extending to any value of between this. So this number, or if it is n, cannot be analyzed. But for this one, it's going to be finite number of coefficient. For example, from coefficient number 1, as you saw it in your frequency, I mean the discrete time domain. Here, for example, if you want to say the relationship here, there is we have seen that numerical operation, one side can be easily analyzed using numerical, and another one cannot be can be obtained, for example, for DTFT. So if you say, for example, x of k, for example, any value of x of k, or x counted from, for example, from x of 0 up to x of any value from x of x of n minus 1. So this one can be there's a form of finite set of data that can be analyzed. But if you say it is infinite, for example, if it is k of j omega, this case it is harder to be analyzed to their frequency. Of course, if you want to obtain from again this value, so this is going to be DTFT, and the other one, the first number is good. So this is relationship. So it is not pure to get this one of omega, for example, to their corresponding x of n. This is very hard in terms of numbers. So these are the relationship in terms of numbers. So we have discussed we discussed some of the main points here. We said first of all we are discussing the Fourier discrete Fourier transform, which is DFT. We discussed also the IDFT, which is its inverse. We have also discussed their comparisons. We have discussed the relationship. Now we are going to discuss the properties. Properties are the same as we have seen even at the Z transform, or some from introduction, the way how some of the scaling properties of DSP and how the signal properties that we have seen. Here also is going to have the linearity property. It's going to have the time shift property and the frequency shift properties. We also have the convolution, the circular convolution in this case. We are going also to have a multiplication property. We have also Factorable Theorem, and so on and so forth. Those are the properties. They are like, for example, like 6. So maybe I have to highlight them for you so that next time when we are giving examples, you can easily remember what we highlighted. So it's very important to note that these properties, for example, if you are trying to relate them, it will be easier for you to identify if given any calculations or any given number, you can easily know which methodology you are going to use or which property you are going to use and which comes in your mind. So maybe I can just highlight them. So there is number one is going to be linearity. Number two is going to be time shift. Shift. Number three is going to be frequency shift. Frequency shift. Yeah, we can also have the Satchel convolution shift. The Satchel just bringing two signals together, you have to do a convolution sum. In this case also, you can combine them. For example, you can have x of k, x of k times x of another, x of k. Then you can have y of k together, bringing them. For example, having, any signal from discrete value, for example, a signal represented by M1, M2, M3, or another signal represented by N1 to any value, then combine them, bring them. It is very useful to combine them by using Satchel convolution. We can also have a multiplication property. Multiplication property. You can also have the Factorable Theorem. This Factorable Theorem is the other one of having some values, but you have to have a repetition, many repetition of those ones, from where you can have exponential values of x squared, for example, in this case. So it's going to have a double check from one position from infinity, then from in between. For example, if you have some values here, then you can consider one part or you can consider another part. So in this case, you decide which value you can determine by using each one of these properties. So if I can go one by one, remember we said if you have x of n, x1 of n, a signal, combining the signals in a linearity form, you expect to have, for example, y of 1 of n. So if this, for example, if you have x1 of n, you expect to have y1 of n. That is a linearity. It's going to be in that way. So, and if you are computing, for example, big X of k, for example, in this case, if it is a frequency, it should be y, for example, k, the same way. That is what we call a linearity. And if there is any coefficient that has been multiplied, for example, put an A here or a B somewhere, then it's going to be done also on the right-hand side. So what is done on the left-hand side is going to be the same thing on the right-hand side. So that is a linearity. And if you come up to the point of time shift, remember we are talking about the way how you can, for example, if we say time shift, for example, if you say x of n can be n minus m. These are the values, n numbers. So that one also can be transferred to its, for example, any summation from n 0 to 0, So the other one big X of k n times the other one. But remember, in this case, you are going to combine both signals. So instead of, for example, j2 pi, it's going to be k minus, for example, n or m, something like that. So okay, minus m in this case. So that is a shift theorem. And also you can have also the frequency. Frequency is nothing but you are going to change x of n into their corresponding, x of n. Remember, when you're putting into their summation at this n, you can put omega, j2 pi, remember, 2 pi kn over big N, which can be demonstrated like big X of n minus m in this case. So you are shifting. So it is shifting between two numbers, big N and X of n. So I'm trying to explain. One is linearity, another one is a time shift. So another one is it's a frequency shift. This one, the big ones. But also convolution, that one also I talked about. Suppose if you have signals like n and m, and then all any values for example, then you can have this b squared also. So this one also is very common. So those I was just explaining the properties of DFT, but also without even just trying to compare. For example, if you are given any number, even without even explaining that use this method or any tool, you can easily know which side. So wherever you see all these comparisons, or big omega or small omegas, you will understand whether the signal is in DFT or it is in IDFT. So these things are very common. So in this case, for example, there are some examples here that we will also have to perform, and we will also continue by taking the examples from by applying these properties wherever, and show it how you can easily identify. So remember, in all engineering subjects, everything has a reason. It's not like just competing anyhow, because if you use the way how you think it should be, then you will not get output. So suppose if you are using any hardware component and you want it to be, you use a long one, of course you can understand you will end up just getting the poor results or the unexpected results. So likewise here, you have to be conscious and careful to understand all these concepts, so that if you are given any problem to solve in engineering, you will know which property you are going to use, which tool you are going to use, and which methodology you are going to use. So it is very important. Another thing that I wanted to note in this lecture of today, you remember from the beginning the behavior of the signal. How, so you remember you are talking about the DSP and every word that repeats there and then and every time is a signal. So we are analyzing the signal. So remember, we are processing the signal. So the signal behavior should be understood in this case, so that when analyzing any particular signal, be it a discrete time signal or be it a frequency domain, should be understood and see its behavior by considering the behavior of each and every signal, and by applying some of the tools that you that can help you to obtain the output. Yeah, another thing is just to remind you, remember the signal and in different formats. For example, if we are to use, for example, unit step, step signal, or ramp signal, or any format of signal, exponential signals, or electrical signal. All these behaviors should be also be your daily habits to understand them. For example, if you want to relate it to other engineering subjects, for example, where you have to understand the power signal, how power is derived from its, for example, the current, the power, the resistance, if you want, for example, in electronics. Remember that our computing devices are made of electronic complex values. We will also require some of the complex values notation, for example, bringing us to trigonometric relationships, so values, bringing in some, sine waves or cosine, to bring some relationship, for example, of E, for example, E omega becoming cosine omega plus or j sine omega, like this. So we bring in cosine formula and sine formula in this case. So this is very important. And remember, if you have cosine, you can also easily derive this E terms. So, and that one is also what we call Euler's formula. For those who have studied mathematics, you remember what is called Euler formulas. Just obtaining E power j omega assigned. So these things to analyze frequency domain or the time discrete domain are going to be occurring in our daily calculations. For example, if we want to calculate any value, for example, given any number, and then you want to calculate, for example, omega n at any, okay, we have this omega n kn. So if n is equal to 0, of course he is going to be 0, and the value, of course, any number over z is going to be, okay, any value is going to be 1. So the first term is going to be 1. The second term is going to be supplied with supplying 1 if we are using these trigonometry values, and so on and so forth. So I suppose now our property is now here, because we are using a flip chart, but it's going to be seen in your notes. So I was talking about the unit step, just to supply some of the values there, having the other formats that we used, but also we can use what we call, remember in our outlines we used to say, for example, how does using a matrix format look like? For example, if you have value in this case and you want to put into the matrix 1, 1, so 2, 2, 3, 4, 5, like that in the matrix format. For example, if it is 1 by m by n format, for example, to formation of matrix, how do we use it using the x frequencies, having a batch of frequencies? So that is a matrix format. We can also have the computation of total DFT and IDFT, having some numbers. Of course, you remember the big N and some small n. So next time I think we shall discuss the properties into details. How do they behave using symmetric and periodic properties? That's what we are going to study for our next lecture. We also have to study about the transformation of how do you convert the unit step signals to their equivalent or to their corresponding matrices. So this is very important. We also have some tutorials and discussion. And I remember my students, I think they may have. For those who don't have, maybe you can again request from me, from my contacts, as I say. So next time is going to be a full of calculation and showing how you can obtain the values or the output. So all these are going to be, next time we are going to calculate one by one and showing these were the words and some equivalences and the relationship. So we are going to use these relationship and properties in our calculations. So this is very important. So we discuss about how we calculate using these properties. As I have mentioned, we are going also to discuss according to their matrices format, and also we are going to see the algorithm that we can apply. So this is very important to note. We also remember in our outlines. Remember in our outlines we discussed about the convolution, the circular convolution, whereby we had a signal of n and m, then you have to combine and just bring something like okay, this one. You remember this one, where I discussed this one? This one also next time we are going to see their relationship. But in short, it's going to be a circular, so it's going to be in a circlewise, a cyclic format. It's going to be in a circle, embodied in the circle, so that the function of two signals being combined together, you can have a periodic signal, you can have the periodic signal, then they can be brought together and be converted or summed or just added together to make a signal. So that was a circular convolution. And remember, the normal signal for circular convolution, remember, it's like applying the multiplication or a star signal that they will be appearing it's not a multiplication, but it is just trying to show you the union or link between two different signals. So suppose if you have two signals coming from the other end, another one coming from the other, there is something that is uniting them or just joining them together to bring them together to be one thing. That is convolution, and it's very important in our signal processing, because you may have two different signals, but you want to put them in a system whereby, for example, you are using LTI system to come up with some of the domains. You can also have different signals, for example, in a time domain or frequency domain. Then you combine them by using circular convolution. Then you can obtain some of these very important. So brief me, and next time we are going to have some of the calculation. Today we have talked much. We have but it was very, very important to let you know some of the terms that we use in DFT. Also together we discussed the reverse or inverse of it. So next time it's going to be calculation a little bit. And remember, some of you have my studio numbers with some of the solved problems, but together we can share some of these videos whereby you just see watching through my YouTube channel and just try to make subscription. Then you just say like, share so that your friends also can see. So thank you for today. Today it was amazing lecture, and then we hope even the next lecture will be fantastic. Thank you for watching, and thank you also for your contribution. Thank you. Bye.